Matrices. So if you've taken a class on matrices before, you probably, like me, had a difficult time getting through it. And that's because for the most part, matrices are presented as a very mathematical construct with different rules for multiplication, and it was very difficult to make a real-world connection of what a matrix really is or what it could be used for.
Unfortunately, no one can be told what the matrix is.
Now, it turns out in business analytics, matrices form the underpinnings of many of the most powerful tools that we have for high-dimensional data analysis and, as we'll see, for calculating conditional probabilities via Markov chains for pretty complex scenarios. So there's really no way around it. A matrix really is a mathematical construct that sometimes has nice analogies to data sets that we see in business analytics. It's just something that we have to learn in order to appreciate how some of these tools in business analytics actually work. Now, as to the ins and outs of how to think about matrices and what matrices are, I'm going to point you over to Grant Sanderson, the 3 blue, 1 brown guy, because he has a series of videos that are absolutely amazing in terms of really understanding the guts of matrix algebra, matrix multiplication, and what matrices are really doing. For the most part here, all I want to do is point out some of the major operations that we can use on matrices and how they'll apply to business analytics tools. So let's start out by just talking about resources that you can go to if you do have difficulty in comprehending some of these topics. 3 blue, 1 brown, I think, is a great source for understanding at a fairly high level what matrices are all about. If you need practice doing computations or coming up with exercises that test your strength when it comes to matrix algebra, going over to the Khan Academy and looking over some of their selection of classes, their introduction to matrices, looking at systems of equations in terms of matrices, I think that's very helpful as well. So let's talk about what a matrix is and how it relates to business analytics. Now, I like actually thinking of a matrix as a data set, because a matrix is a two-dimensional construct. It has rows, it has columns, much like a data set that we would open in Excel would have. So it's kind of like a generalization of a vector, which is just a one-dimensional array of numbers or text, just giving it a second dimension, kind of giving it length and width here. So very often we'll just call our matrix capital M, and the way that we'll represent the matrix itself is by drawing a massive set of square brackets and then populating the rows and the columns of that matrix so that it looks very much like a data frame. So how do we refer to the elements of a matrix? Well, we're going to refer to them much like we refer to elements in a data frame, by their row number and their column number, the combination of those two. So what we're going to do is going to give subscripts to the name of our matrix, I and j. The very first number in that subscript is going to refer to the rows, up and down. The second number is going to refer to the columns, left and right. Much like when we refer to an element in a data frame, we put on the square brackets, we put a comma in those square brackets. The number to the left of the comma represents the row number, and the number to the right of the comma represents the column number. Same sort of convention when it comes to referring to positions inside of a matrix. So if I wanted to ask, hey, what's the 4-3 element of a matrix? That means 4th row, 3rd column, 4th row, 3rd column, we see a 6 there. So when we talk about the dimensions of a matrix, we refer to the number of rows followed by the number of columns, R and C, let's call them that. We refer to it as an R by C matrix. So this would be a 4 by 3 matrix because 4 rows, 3 columns. Now, how do we get a matrix defined in R? Well, we're going to use the command matrix. The first argument is going to be a vector of numbers that we want to have populating the matrix, and then we're going to give 2 additional arguments. We're going to have either n row equals or n col equals that specify the number of rows or columns. You only have to specify 1. And then we'll add in the argument by row. And this will either be true or false, depending on if you want those matrix elements to be populated from left to right, then top down, kind of like how you would read a book, or if you want to do it column by column. And my mind works populating the matrix from the top row, left to right, as if we were reading a book, going on to the second row, etc. So by row equals true would be the way that I would set up the matrix. But I have two examples here of how the by row equals true and false result in the appearance of the matrix depending on what's been set up. So after we've defined a matrix, well, there's going to be a whole set of terms that we use to describe what that matrix looks like. So we might say that a matrix is diagonal. What does that mean? That means that all of the entries are 0 except for the ones on the diagonal of that matrix. So we have to have a square matrix, equal number of rows and columns, for there to be a diagonal. A diagonal matrix would be a square matrix with non-zero entries only along the diagonal of that matrix. Then we have upper triangular and lower triangular. And these will be terms that you'll run into in the 531 class, the optimization class, because very often we like seeing systems of constraints written so that we have upper triangular or lower triangular form. What does that actually mean? Well, upper triangular means that the only non-zero entries are in the upper right part of the matrix. Lower triangular, the only non-zero entries would be on the lower left part of the matrix. An invertible matrix is one that has an inverse, more on that later. Positive definite, negative definite refer to the eigenvalues of the matrix, bigger than 0, smaller than 0, etc. More on that later as well. But those are some of the key terms, a nice useful slide to reference back if you need to review what those terms mean. So in business analytics, we typically do stuff with matrices. It's not like a data frame that just kind of sits there and we make plots on it. We add matrices, we multiply matrices, we do some algebra on the matrices themselves. Now, addition proceeds pretty much as you would expect. If you had two matrices and you wanted to add them together, well, number one, they have to have the same shape, because the way that we add two matrices together is to just do element-wise addition. So the upper left element of the sum of two matrices would just be the sum of the upper left elements of both. So no problem. If you want to multiply a matrix by a number, a single number we refer to as a scalar in mathematics, take this matrix, multiply it by 2, that just means that every number inside the matrix gets multiplied by 2 as well. So how would we do this in R? Well, if we define our matrix A to look like this, 2 rows and 4 columns, then we could multiply each element by, say, 3, just by saying 3 times A. If we defined another matrix B that had the same size as A, 2 rows and 4 columns, we would be able to add them together just with A plus B. And each element of the addition would be the sum of the corresponding elements of the two matrices going into the sum. Now, if we defined a third matrix C here, a square matrix with 2 rows and 2 columns, if we try to add two matrices that can't be added together, two matrices that don't have the same shape, R will let us know and it will say, hey, you're dealing with some non-conformable arrays. They don't have the same shape for that mathematical operation to be applied. So addition, multiplication by a scalar, really nothing all that mind-blowing. What's really different when it comes to matrix operations is when we do matrix multiplication. Now, there's a nice little algorithm that you can use to hand multiply matrices together. I'm not going to be worried about that because we can make R do that multiplication for us. But it turns out that the operation behind matrix multiplication crops up in a variety of business analytics contexts. Specifically, if we want to start doing conditional probabilities and that partitioning trick that we've discussed, it turns out that the math behind partitioning looks very similar to the math that's required to multiply two matrices together. So how does this work? How do we multiply two matrices together? What is it actually doing? What's the procedure? Let's do it. So number one, just like when we're trying to add two matrices together, we can only multiply two matrices together when they have the right set of shapes. So with addition, they have to have the same shape, the same number of rows and columns. For matrix multiplication, there's a slightly more complex relationship. Namely, the number of rows and number of columns across the two matrices have to match up in a special way. So if A is a n by p matrix, n rows and p columns, and we want to multiply B to that matrix, let's say B is a matrix that has a certain dimensionality, then we have to ensure that the number of columns in A matches up with the number of rows in B. So the number of columns in B is irrelevant, the number of rows in A is irrelevant. We just need to make sure that when we're multiplying two matrices together, the number of columns of that first matrix is equal to the number of rows in that second matrix. Now, what's going to be the dimensionality of the matrix that results from that product? Well, if you were to write out the dimensions of the two matrices involved, those two inner ones have to match up. We can kind of effectively cancel them out. What's left over is going to be the dimensionality of the matrix resulting in from that product. So how do we actually get what the elements are of that product? Well, it's a mathematical procedure. There's no ins or shortcut about this. In order to figure out a particular value in the matrix product, say the value in row I and row J, we have to sum up a bunch of products. There we take one term from the A matrix and another term from the B matrix. So once again, I'm not going to worry too much about actually doing this by hand, but essentially we'll be taking a row of the A matrix, a column of the B matrix, and multiplying stuff together and adding up the results. And the weird thing about matrix multiplication is that it's non-commutative. If you do A times B, you're probably going to get a different matrix out than if you had done B times A. So procedurally, how does matrix multiplication work? Well, here are two matrices that can be multiplied together because the number of columns in that first matrix is matching up with the number of rows in that second matrix. So 2 columns, 2 rows, we're good to go. The result will be a 3 by 4 matrix. So the way that we figure out, okay, what are going to be the entries of that result, we'll multiply a particular row of the first matrix by the column of the second matrix. We'll calculate what's known as the dot product of these two vectors here. We'll take the first element of the row, multiply it by the first element of the column, then add that to the second element of the row multiplied by the second element of the column. There we go. So we'll just repeat that procedure for every row column combination pair until we get our result. So there's some useful diagrams that I found online for kind of schematically showing how that matrix multiplication proceeds. I'm going to put in a quick little animation of how I remember how to do it here. All right, so like I was saying, matrix multiplication isn't necessarily commutative. You might get a different result when you do A times B than if you do B times A. And here's an example. Here we got an A matrix, a B matrix. If we throw these together in terms of multiplication, here's the matrix that comes out. But if we just reverse the order of those matrices, we'll get a different matrix out. And in fact, sometimes if we swap the order of the matrices in the product, we can't even do the matrix multiplication at all. Those matrices are going to have the wrong shape. So what exactly is going on, though, when we multiply two matrices together? So we know there's some complex mathematical procedure for figuring out what the result is. Well, when we multiply two matrices together, we're basically just performing some sort of rotation and potentially a projection into a higher dimensional space or a lower dimensional space. So what do I mean by that? Well, if I'm taking this matrix here on the left, this 1, 0, 2, 1, if I treat this as a data frame, then each individual is represented as a row in the matrix. So this would be a data set with two individuals, each having two characteristics that have been measured. So characteristic 1 has a value equal to 1 for the first person and 2 for the second person. Characteristic number 2 has a value of 0 for the first person and 1 for the second person. When I multiply the data matrix, which I'll call it, by this other matrix, that just corresponds to essentially rotating the positions of these individuals in the data space. If I anchor each individual to be at the origin of the plot at 0, 0, and represent what an individual looks like as having an arrow pointing out to the location in space, so like an x of 1, a y of 0, x of 2, a y of 1, this matrix multiplication is just rotating that vector somewhere. Now, in this case, if I have three individuals, each of which has two characteristics measured, if I multiply that by a matrix, I see I'm getting a much bigger matrix. But what's going on is that I'm still dealing with those three individuals, but the characteristics have just been rotated and actually projected into a higher dimensional space in this case. Instead of having two characteristics of each of those individuals being recorded, or each of those three individuals being recorded, I now have four characteristics of those individuals recorded. What are those two additional characteristics that are making me go into this higher dimensional space? Well, they're just linear combinations, weighted sums of the two characteristics that I know. So it's kind of like I'm just adding in more variables, doing some feature engineering, taking what I already knew about the individual and just kind of rethinking what those characteristics are telling me. Kind of like converting from Celsius into Fahrenheit and maybe doing something fancy like taking 2 Fahrenheit plus Celsius, creating a new variable that contained that, and maybe a fourth variable that's 10 times Fahrenheit minus 20 times Celsius. So sometimes this matrix multiplication is just like you're adding in new variables from what you already know about those characteristics. And in business analytics, we do feature engineering all the time. We take the characteristics that we know and we create new features that may be helpful in making predictions or understanding what's going on in the data. So how do we do matrix multiplication in R? Well, we need a special symbol for matrix multiplication. If we just do A star B, that's going to do element-wise multiplication. It'll take the upper left element of A and multiply that by the upper left element of B to give the result. If we want true matrix multiplication, we need to surround that asterisk, the multiplication sign, by percentages. So A percent star percent B is how R is going to multiply two matrices together. Now, if you try to multiply two matrices of the wrong shapes, you're going to get that non-conformable arrays. That's always just telling you that, hey, the shapes of your matrices aren't right. For matrix multiplication to work, the number of columns in that first matrix just needs to match up with the number of rows in that second matrix. Otherwise, you get this error. All right, now if we just deal with numbers, we can talk about, say, the reciprocal of a number or the inverse of a number. What do we need to multiply a number by in order to get 1 out as the result? So what's the inverse of 10? 1/10. 10 times 1 over 10 equals 1. What's the inverse of 1/7? Well, 7. 1/7 times 7 equals to 1. So it'd be a natural thing to ask, okay, well, what's going to be the inverse of a matrix? Well, I guess I should define what 1 is in terms of a matrix. 1 we're going to refer to as the identity matrix, basically a diagonal matrix that's square that only has 1s along the diagonal and 0 everywhere else here. So if I'm going to talk about a matrix inverse, I want to figure out, well, what's the matrix that I want to multiply by in order so that the result equals to the identity matrix. And we're going to denote the inverse of a matrix by taking the matrix name and raising it to the -1 power. Now that's not a literal raising it to the -1 power, taking the reciprocal of the matrix. That's not an actual operation. That's just going to be how we represent a matrix inverse. Now, there's no easy way to do this by hand, except for like 2x2 matrices, but in R, it is very easy to actually get. So if you want to know, well, what's the inverse to your matrix A, you just say solve A. Now, because there is some mathematical procedure that R is going to use to try to figure out what this matrix is, the answer is going to be subject to machine precision. So here's a matrix B. I'm asking for the inverse of B. Notice some of these elements are basically 0, -8.88 times 10 to the -17th power. Because of the mathematical procedure R uses to get these inverses, zeros are going to appear as just very, very tiny numbers. And so if you run into something with a tiny, tiny exponent here, then you can, for all intents and purposes, just ignore those. Notice if I were to take B and multiply it by its inverse, I get 1s along the diagonal and 0s other places. This one actually looks like a 0. This one is basically 0, 8.88 times 10 to the -17th power. So inverses are actually used all over the place in actually solving systems of equations, figuring out what the solution is to the coefficients of a least squares regression. Matrix inverses and quickly computing matrix inverses are one of the most popular problems to actually deal with in analytics and other fields of learning. Now, another property of the matrix that we want to be familiar with is the transpose of a matrix. And that's just basically reflecting the matrix across the diagonal. If a matrix starts out with n rows and p columns, well, the transpose of the matrix is going to have p rows and n columns. It's like a mirror image across the diagonal. How do we get the elements of the transpose? Well, we can basically say that the ijth element of that transpose is just the jith element of the original matrix. So just swap the positions of rows and columns. So if A is this matrix right here, flipping it across the diagonal, we would end up with this matrix. So 3 rows, 2 columns becomes 2 rows, 3 columns here. How do we denote that? Well, we put a little t as a subscript, or maybe a little prime up in the subscript to denote the matrix transpose. And transposes are really quite useful in least squares regression, figuring out what the solutions are for the coefficients in a least squares regression. How do we get the transpose in R? Well, the function is just t. So t parenthesis A is going to give us the transpose of that A matrix. So if you love matrix math, no one really does. I have some slides in here that tell you, hey, here's some cool math you can do with transposes. We're not really ever going to need it. We're not going to be deriving results from square one. We're really just going to be using the results that other hardworking people discovered for us and seeing where that's applied in business analytics. So one thing we've mentioned is the identity matrix, useful for thinking in terms of matrix inverses, and also diagonal matrices, matrices that only have non-zero elements across the diagonal and 0 everywhere else. There's a quick way for making one of these diagonal or identity matrices in R, and that's with the diag command. So if I were to say diag 1, n, that would create an n by n identity matrix. If I wanted a diagonal matrix with just arbitrary elements across the diagonal, what I could do is I could set up a matrix full of zeros, n rows, n columns, and then just say diag A equals to the vector of diagonal elements that I want there. So making those identity matrices, making those diagonal matrices not too bad in R. Now, matrices have some very important properties that you're going to want to know about going forward into future business analytics classes, specifically what the rank of a matrix is. And we'll actually use this in 533 when we talk about multivariate probability distributions. So there are two types of rank when we discuss matrices, a column rank and a row rank. Now, the column rank is just the number of linearly independent columns that the matrix possesses. So what do I mean by linearly independent? Well, two values are linearly dependent if we can write one as just a weighted sum of the other. So in this case, if I'm dealing with the matrix A, I can say that the third and fourth columns are not linearly independent because I can write the numbers in this third column as just 3 times the first column, plus 0 times the second, plus 0 times the third. So I can get the values in the third column from the other columns. They're not linearly independent. Likewise, the fourth column here, I could get that as taking 2 times the first column, adding 1 times the second column, then plus 0 times the third column. So in this case, I have two columns that are just weighted sums of the other columns here. So we would say that this has a column rank of 2. So these two kind of stand alone by itself. There's only two columns that I can't get by just taking weighted sums of the others. So column rank actually plays a very important role when it comes to doing a linear regression, predicting y from a set of predictor variables. So if we think of the matrix as a data frame, each row is an individual, each column represents a characteristic of that individual, either the y variable, what we're trying to predict, the x variable, our predictor variables. Then it turns out that we can only find the solution to the least squares regression equation if we're dealing with a data matrix that is full column rank. Basically, each column is linearly independent of one another. So in order for us to come up with a solution to that regression, we just need to make sure that none of those columns are redundant. We can't just get the values in a column by taking weighted sums of the other columns. So in other words, if I was predicting sales of a product, say from the temperature outside, I wouldn't want to have two columns, one for Celsius and one for Fahrenheit. Yeah, Fahrenheit and Celsius is related by just a linear transformation. That's going to cause my least squares regression to fail. I need to ensure that my column rank is equal to the number of columns that I have in the data. Now, the row rank of a matrix is a related construct. It's just the number of linearly independent rows in your data, in your matrix here. So consider this matrix with 3 rows. This only has a row rank of 2 because I can get the values of the first row by just taking a weighted sum of the values in the other. If I were to take 1/2 the second row and add in 0.8 times the third row, well, that's going to give me the top row here. So one of those rows I can get from just a weighted sum of the others. This only has a row rank of 2. So if we're dealing with a square matrix, the row rank and the column rank are going to be the same value. If we're dealing with a non-square matrix, we're going to say that the overall rank of the matrix is going to be the smaller of the column rank or the row rank. And so when we typically do talk about the rank of a matrix, we're talking about the smaller of those two ranks. And when a matrix is full rank, that means its rank is the largest possible value it could have been based on the number of columns or rows, the smaller of those two. So when we have a square matrix, we say it's full rank when the rank's just equal to the number of columns or the number of rows. If we're dealing with a non-square matrix, it's going to be full rank as long as the rank equals to the smaller of the number of rows or columns here. And for linear regression to occur, like what I've been saying, the data matrix has to be full rank. So we have to have more individuals than characteristics. We need more rows than columns. And then we also need to make sure that the columns are all linearly independent of one another. All right, how do we find out the rank of a matrix in R? Very tedious to do by hand. Well, if we load up the matrix package with the capital M, we can ask, hey, what's the rank matrix of that? Rank matrix of the command. If we just say as.numeric of that, it'll print out what the rank of that matrix is. So in this case, it's saying, okay, well, A has a rank of 2. That means that, okay, it's not full rank, because if there's going to be 3 rows here, well, 3 is not equal to 2. It must not be a full rank matrix. And actually looking a little bit ahead, you can tell when a matrix is not full rank if you get its determinant. If you take the determinant of a square matrix, if it's equal to 0, it's not full rank. If you're dealing with a non-square matrix, if you take that matrix, multiply it by its transpose, if the determinant of that is not, if that is equal to 0, you're dealing with a matrix that's not full rank here. So why does rank matter? Like we were saying, in least squares regression, we have to have a full rank data matrix in order to find the solutions to the least squares estimates. If you're representing a system of equations, like what you might do in linear programming, as a matrix, in order to have a solution, or to not have infinite number of solutions, you have to make sure that that matrix is full rank as well. And it turns out that many algorithms and tools in our toolbox in business analytics deal with matrices, and most of them end up failing unless your matrix, some matrix related to that problem, is full rank. So this tends to work its way into a lot of various aspects of business analytics. And what is R like saying when you're not dealing with a full rank matrix? Well, R likes to say that you're dealing with a singular matrix. That's R code for, hey, dummy, your matrix isn't full rank. I'm not going to be able to do what you want me to do. Another characteristic of a matrix, besides its rank, is the trace. This one's easy. Just sum up all the diagonal elements, and that's going to be the trace of that matrix. Obviously, it's only going to be relevant to square matrices here. And there's some mathematical coolness properties of traces if you're curious. Now, the determinant of a matrix is another characteristic that is useful kind of as a byproduct for a few different things. Looking at the determinant can actually tell us quite a few things about that matrix. I just mentioned that if the determinant of a matrix is 0, we know that the matrix isn't full rank. But also turns out that if the determinant is 0, we're not going to be able to invert that matrix either. So what is this determinant? How is it calculated? What does it represent? Let's have a go at it. So number 1, determinants can only be calculated for square matrices, equal rows, equal columns here. We denote it either by det of A, which also happens to be the function you use in R, or by surrounding A with some vertical bars. Kind of looks like the absolute value sign, but when we're talking about a matrix, that symbol just means the determinant of the matrix that we're talking about. So how do we actually get it? How do we visualize it? Well, it turns out that with a 2x2 matrix at least, the determinant of that matrix is the area of the following parallelogram. If we treat each individual in this matrix as kind of a row, kind of treating it like a data frame here, individual 1 has characteristics A and B, individual 2 has characteristics C and D. If we anchor both individuals at the origin of the plot, and then draw an arrow out to where they're located in the data space, their x and y coordinates. And then if we kind of add those two vectors together to make a parallelogram out of it, it turned out the determinant is the area of this shape. All right, I guess that's cool. Geometric interpretation. If we had a 3x3 matrix, it turns out that if we did something very similar, treated each row as an individual in our data matrix with 3 different characteristics, put an arrow out to where that individual pointed in space, kind of extended those so that it made a parallel pipette. I think that's how it's pronounced. It would be the volume of that shape in that 3-dimensional space. So we can think of the determinant as the area, the volume of some shape that's defined by that matrix. And there's a mathematical procedure for going and actually getting a numerical value for that. Very useful actually if we have pairs of random variables, pair of random quantities, and we want to measure something about them, like measure the sum of the squared values of those 2 random quantities. To go from one scale to another, from one set of quantities to a different set of quantities, we actually need to know the determinant of a matrix that is used defining those transformations. So that's one place we use it in probability. It's also used in multivariate probability distributions like the multivariate normal that we'll eventually talk about. So here's an application. Here's something that's a little bit related to your optimization class 531. What if we wanted to solve this system of simultaneous equations? We have three unknowns, x1, x2, x3, and we have three equations that relate these values to each other. Well, what we could do is we could relate the left-hand side of these equations to a matrix. In fact, we can just take the coefficients of those variables x1, x2, x3 and have those be the elements of the matrix. Now, here's where the determinant comes into play. If we take the determinant of this matrix and we find that it's not equal to 0, that means there must be a solution to this set of equations. If the determinant is 0, there's either no solutions or an infinite number. And so because this determinant of this matrix is equal to 45 in this case, we know there has to be a set of values of x1 and x2, x3 that solve this set of equations. How could we get those solutions? Well, we could rewrite that system of equations just in matrix form. If we have our A matrix to be the coefficients of the x1, x2, x3, have an X matrix just be a 3-row, 1-column matrix containing x1, x2, x3, we could convince ourselves by hand doing the matrix A times X. We'd actually get something that looks like this. We could set up the matrix equation A times X equals B. B is a matrix of the values we find on the right-hand side. And then we can just do a little bit of algebra. We want to solve this equation for X. Well, how can we do that? Well, in this case, we can left multiply both sides of the equation by the inverse of A. Now, remember, the ordering of matrices in matrix multiplication is important, so we have to specify left multiply versus right multiply. So as long as we do the same thing to both sides of an equation, we're usually good to go. So if we multiply the left-hand side and the right-hand side by A inverse, that's an okay thing to do. But then the inverse of a matrix times the matrix itself is always the identity matrix. The identity matrix times something is always that something. So we can solve that system of the simultaneous equations by taking the inverse of that A matrix and then multiplying it by the matrix, giving the values on the right-hand side of those equal signs. So easy enough to solve that. There's some mathematical properties that are cool with determinants. There for those that love that kind of stuff. But let's talk about some matrix algebra. It turns out that occasionally in business analytics, we have to do algebraic manipulation, solving equations that deal with matrices. So matrix algebra works a little bit different than just the algebra that you're used to, mostly because the matrix multiplication is not commutative. So you have to be really careful about left multiplying versus right multiplying. That's something you didn't have to worry about when you're just dealing with normal sets of equations and normal numbers here. So let's imagine that we wanted to solve the following matrix equation. A times B equals C. Well, if these were numbers and we wanted to solve for A, this would be pretty easy. Just divide both sides by B. A would be equal to C over B. Well, there's no such thing as matrix division here. There's only multiplication by matrix inverses. So if I wanted to get A equals to something, I need to get rid of this B on the right-hand side. So what could I do? Well, I could right multiply both sides of this equation by the inverse of B. If I were to do this, the B times B inverse is going to equal the identity matrix, and then A times the identity is just A. So C times the inverse of B, done, solved it. All right, well, what if I wanted to solve this equation for B instead? Well, if A is a square matrix, then I could left multiply both sides of this equation by the inverse of A. A inverse A would be equal to the identity matrix. The identity matrix times B would just be B, and I'd have my solution. Well, what if I had a more complicated situation where I didn't necessarily have square matrices? What if I had the equation A times B equal to C, but none of these guys are necessarily square matrices, and I wanted to solve this equation for A? Okay, well, I can only get the inverse of a matrix if it's a square matrix, so what do I do? Well, here's a cool trick. It turns out that if you take a matrix, multiply it by its transpose, the result is always going to be a square matrix. So that gives me a way in. Why don't I go ahead and right multiply both sides of this equation by the transpose of B? Same thing to both sides of the equation. That's an okay thing to do. What's great is that B times B transpose is now going to be a square matrix, so I could further multiply both sides of this equation by the inverse of B transpose. So once I do that, well, I have a matrix, B transpose. The inverse of that matrix, B transpose, that's going to be the identity matrix. A times the identity is just going to be A. So I have a fairly complicated matrix equation that lets me solve for the matrix A in this equation right here. It's a little bit about how matrix algebra works here. You can actually do differentiation with respect to matrices. It's really tricky stuff. If you went on to get your PhD, you might have to do that. Tricky stuff, though. So let's relate this to something that we actually do in business analytics all the time. Basically fit a least squares regression line to a set of data. So we have some y variable that we want to predict, something like sales, and we have a bunch of predictor variables. So a linear regression says, okay, well, I'll predict your sales by coming up with a weighted sum of those predictor variables. We just need to figure out what the weights are. Or more in regression speak, we need to figure out the coefficients of those predictor variables so that when we take that weighted sum plus the intercept, we get our answer. So we can represent the least squares regression problem as a matrix problem. We can define the matrix Y to be a matrix with just a single column and n rows, giving the n y values of the n individuals in our data set. And then if we define the X matrix to be having the first column 1, the second column being all of the x1 values of all the individuals, the second column being the third column, being the x2 values of all the individuals, etc., etc. Then, if we define the matrix beta to be just the matrix of the coefficients, and epsilon being the matrix of the disturbances, how far off the individual is away from that straight line, we can actually write the regression model in matrix form as follows. And okay, if we wanted to solve this equation, basically figure out what should the betas be in order to minimize the sum of the squared errors, well, we can do that. It turns out that if we wanted to minimize the actual values of y minus the predicted values of y from the regression squared, minimize the sum of the squared errors here, that would correspond to minimizing the result of taking this matrix product. Basically, the actual values of y minus the predicted values of y. If I take that transpose, multiply it by itself, it's like squaring the residuals, the errors made by that regression model. So, okay, what that boils down to, after a little bit of matrix calculus here, is figuring out how can I solve the following equation. Y minus x times beta is equal to 0. So, just rewriting that, this is basically the least squares problem. I need to solve this equation for beta. I need to figure out the weights in that weighted sum that's going to come up with the best fitting line. So how do I do that? Well, X isn't going to be a square matrix, but I can make something a square matrix if I left multiply both sides by X transpose. So X transpose X beta is going to equal to X transpose Y. Well, X transpose X is going to be a square matrix. So I can take its inverse and left multiply by that inverse. So X transpose X inverse times X transpose X, that's going to be the identity matrix. I have the same thing on the right-hand side of the equation. The identity times beta is just the beta, and so I find the solutions to my least squares coefficients, the weights in the weighted sum of my predictor variables, that's going to give the overall best fitting line here. So in R, you could go and confirm that, yep, if you fit the least squares regression line with the LM command, typically what we use to get a linear model relating y to the x's, we get the same weights, the same coefficients for that regression model, and if we had just brute forced it by solving that matrix equation. All right, one last thing that we have to sit down and talk about relating to matrices are matrix eigenvalues and matrix eigenvectors. This actually has a really nice correspondence to studying Markov chains and steady-state probabilities, but eigenvalues and eigenvectors play an invaluable role when we have a high-dimensional data set, maybe with hundreds of characteristics that we've measured for individuals, trying to make the problem simpler, trying to project it down to a lower dimensional data space where we're really only keeping track of just a couple of those characteristics. So let's talk about eigenvalues and eigenvectors. So what are these things? Well, we're going to pretend that we're dealing with a square matrix. We're going to call that A. A is going to have an associated set of eigenvalues and eigenvectors associated with it. So what are these eigenvectors and eigenvalues? Well, these are quantities that satisfy the following equation. So kind of throwing this equation there at you. What does this actually correspond to kind of geometrically? How can we add some sort of interpretation to this? Well, remember when we multiply something by a matrix, that's just like rotating that matrix somewhere in the data space. So if I have vectors x and y, if I multiply those vectors by A, by matrix, that just corresponds to rotating that vector somewhere in that data space. So what an eigenvector is it happens to be a very special vector that ends up not being rotated by the matrix A. It's still pointing in the exact same direction it used to be pointing. Now, with matrix multiplication, not only is that rotation going on, but there's an extension or a contraction of that vector. The eigenvalues are just that expansion factor, if it got bigger or if it got smaller. You can have negative eigenvalues, you can have positive eigenvalues, but it's related to how far that vector gets stretched out or inward relating to where it started. If it's negative, it's kind of flipped to the other side of the origin here. So how do we actually get them? Well, it involves solving the following equation. We look at the determinant of the following matrix equation, taking A and then subtracting off a diagonal matrix where the diagonal elements just are equal to lambda here, and then figuring out, well, what are all of the solutions for the eigenvectors themselves and for the corresponding lambdas here. All right, we're not going to worry too much about getting these by hand. We're going to have R do this for us. The important thing to note is that the eigenvector and eigenvalue just have a really nice simple interpretation. Matrix multiplication is just taking a vector, rotating it, and extending it. The eigenvector associated with a particular matrix is just that special vector that doesn't end up getting rotated. The eigenvalue itself is how far it got extended or contracted, or maybe even if it gets flipped to the other side here. All right, so in R, how do you want to get these eigenvalues and eigenvectors out? Well, a few different commands actually do this for you. We can stick with the eigen command. So given a square matrix A, running eigen is going to give us a list of two quantities. It's going to give us a vector of eigenvalues, and it's going to give us a list of eigenvectors. So for every eigenvalue, there's going to be a corresponding eigenvector, and you just match them up one by one. So the first eigenvalue is 3 in this case. That corresponds to the eigenvector defined as the very first column in the output. The second eigenvalue of 2, well, that matches up with the eigenvector described in the second column of the result here. Now, R has a special convention so that the length of these vectors is exactly equal to 1. So take note of that for when we actually discuss doing Markov chains with eigenvectors here. All right, there's some interesting properties of eigenvalues and vectors, which if you go on to classes that we have in the program that deal with high dimensional data analysis, kind of singular value decomposition, projecting from high dimensional spaces to lower dimensional spaces, eigenvalues, eigenvectors are all over the place in this case. So I'll let you worry about that there. But here's a nice slide to come back to when you get there. It turns out that for dimension reduction in statistics, we very much exploit this idea of finding eigenvalues and eigenvectors of different matrices.